Hello again. Thanks for watching this video and studying math with us. Today, as you watch this, it's important that you think about using the buttons on the YouTube because that's what they're there for. There is work ahead, so feel free to play, pause, rewind, and that will help you as you go forward. The topic being discussed here is previously we talked about how we can graph a linear equation in two variables, x and y, and it ends up being a straight line in the plane. And now we're going to talk about graphing a linear inequality in two variables and how it is represented. Let's start with a simple example. So we're going to consider 2x plus 3y less than 6. Now we start with saying, when does 2x plus 3y equal 6? And so I pick points in the table, 0, 2, 3, 0, and plot those points, connect the dots, and that is the boundary for this region, 2x plus 3y less than 6. Now that is the boundary, but we note that the boundary isn't included here because there's not an equal sign. The next step is we use a convenient test point. Since 0, 0 is not on this line, that's a convenient test point, and we say, does 0, 0 satisfy this equation? Well, 2 times 0 plus 3 times 0 is 0, and 0 is less than 6, so that tells us that it's the half plane underneath that curve. So if we were to graph it, then we would make that boundary line dotted because it's not included, and we would say that any point underneath that satisfies that inequality. That's the test point method. Now, often we can use the test point method or are required to graph more than one linear equation, and here we're talking about trying to find the set of points that satisfies this first inequality, which is the one that we just graphed. 2x plus 3y is less than 6, and the other one that we're having now is 3x minus 4y is less than 12. Well, previously we saw that the line 2x plus 3y equals 6 forms the boundary, and it's the set of points that are underneath that line. But now when we plot 3x minus 4y equal 12, again we can use 0, 0 as a test point, and we see that 3 times 0 minus 4 times 0 is 0, and 0 is less than 12, so that's it. But this is an AND condition, which means it has to satisfy both, so that area that is shaded that way is the solution set for that. So, to summarize then, the procedure for graphing linear inequalities: draw the graph of the equation obtained by the given equality by replacing the inequality sign with an equal sign. Then use a dashed or dotted line if the problem involves a strict inequality, either less than or greater than. Otherwise, use a solid line to indicate that the line itself constitutes part of the solution. Then you pick a test point, AB, lying in one of the half planes determined by the line sketched in 1, and substitute the number A and B for the values of x and y in the given equality. For simplicity, it's good to use 0, 0 or the origin whenever possible. If the linear equality is satisfied, the graph of the solution to the inequality is the half plane containing the test point. Otherwise, the solution is the half plane not containing the test point. Now, in many business and economic problems, we're asked to optimize, maximize, or minimize a function subject to a system of inequalities or equalities. The function to be optimized is called the objective function. Profit functions and cost functions are examples of objective functions. The system of equalities or inequalities to which the objective function is subjected reflects the constraints, for example, limitations on resources such as materials and labor imposed on the solution to the problem. Problems of this nature are called mathematical programming problems, in particular if both the objective function and the constraints are linear equations or inequalities. It's called a linear programming problem. And this says that as well, that if the linear objective function is subject to some linear constraints, it's called a linear programming problem. And that's what we're talking about. Now let's talk about then how we would graph a feasible region and find the corner points. So here we have 4 constraints, 1, 2, 3, and 4. Now, when I say x is bigger than or equal to 0, that means I look at the line x equal to 0, which is this one. It's everything where x is positive. Similarly, y bigger than or equal to 0 is the set of points where y is bigger than 0, so it is up here. Now again, all of these constraints have to be satisfied, so there's an and in between every one of them. Then I graph x plus y less than or equal to 6. Here it could be equal to, so the boundary is included, and I get this line. And here I get 2x plus y is less than or equal to 0, and that's going to be this other line. And now what I will do is I'll do my test points and to see, which half planes, but where they overlap, all of these are ands, is going to be this region. And so that is called the feasible region. It satisfies all the constraints, and there are corner points. You can see that corner point is 0, 0. Another corner point over here is found by taking the intersection of y equals 0 and this line here to give me that point. I take 2x plus y equal 8 and x plus y equals 6 to get that one and this one. So again, what we're doing is we're solving a system of linear equations, which is one of the skills that we had. Now, a big theorem in linear programming is that if there is a solution, it must occur at the vertex or a corner point. So what we do to solve these is we graph the feasible region. We find by solving systems of equations the corner points. We evaluate the objective function at each corner points, and then the answer is going to be the corner point that maximizes or minimizes the objective function. Examples are worth a lot here, so let's look at one. This is a production problem. So Ace Novelty wishes to produce two types of souvenirs, type A and type B. Each type A souvenir has a profit of $1 and each type B souvenir has a profit of $1.20. To manufacture a type A souvenir requires 2 minutes on machine 1 and 1 minute on machine 2, and a type B souvenir requires 1 minute on machine 1 and 3 minutes on machine 2. There are 3 hours available on machine 1 and 5 hours available on machine 2. How many souvenirs of each type should Ace make to maximize their profit? Often it is useful to create a little matrix like this, and I'm showing what is the profit per unit for type A and type B, what is the resource requirement for type A and type B on machines 1 and 2, and how much time is available on machines 1 and 2. So the solution process will be as follows. We'll let X be the number of type A products to make, and Y will be the number of type B products to make. Now the objective function here is you want to maximize the profit, which is going to be $1 times the number of type A we make, and 1.2 times the number of type B. So that's the profit function. But these are the constraints. This is the machine 1 constraint with respect to time. This is the machine 2 constraint with respect to time, and we can't make negative numbers of product, and so we do have those bigger than or equal to 0. So what we're going to do is graph the constraints to set up a feasible region, find the corner points, and see what is the value of the objective function at each of those corner points. So here is the solution. So I graph 2x plus y equal 180 to get that line. I graph 3x plus 3y equal 300 to get that equation. I say that x is bigger than or equal to 0. I say y is bigger than or equal to 0. And I look at the space that satisfies all of those constraints. And that space is going to be this one, which means I have to find all of those corner points. So what, for example, on this one, I have to find the intersection between 2x plus y equal 180 and x plus 3y equal 300. I get that point right there. And again, I have to know what that point is. So then what I do is I take all 4 of the corner points that I have, and I put the coordinates in, and I evaluate the objective function there. Now what we want to do is maximize the profit, and we'll see that the maximum profit happens here. So the answer to this problem would be the maximum profit is 148.8, I suppose those were dollars, and it's obtained by type A is 48 units, and type B, sorry, that went off the page, type B is going to be 84 units. Let's look at a second example. So here is a second example. A nutritionist advises an individual who's suffering from iron and vitamin B deficiency to take at least 2,400 milligrams of iron, 2,100 milligrams of B1, and 1,500 milligrams of B2 over a period of time. There are two kinds of pills that are suitable, brand A and brand B. Each brand A pill costs 6 cents and contains all of those values. Each brand B pill costs 8 cents and contains different values. What combinations of pill should the individual purchase to meet their requirements at the lowest cost? Again, a table is useful. We have the brand A pill costing 6 cents and providing those amounts of those nutrients. Brand B costing 8 cents, providing that much, and the daily minimum requirement is this. Again, we're going to let X be the number of brand A, Y be the number of brand B. We want to minimize the cost subject to the constraints. You can't take a negative number of pills, so those have to be non-negativity constraints. But here you see that these are greater than or equal to constraints for this problem. And that means that what will happen is we're going to be looking at, for the first time in what we've discussed today, greater than or equal to constraints. But the approach is the same. We formulate the problem this way. We find the feasible region by graphing all of these. We find the corner points and we evaluate the corner points at those values. So here is what we do. Here you can see I graphed the constraint about iron. Here was the vitamin B1 constraint. Here was the vitamin B2 constraint. X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. Now where these overlap is in this region up here. And so what we see is that we have 1, 2, 3, 4 corner points again. Now I solved those equations simultaneously to find solutions, and I evaluate the objective function here. But remember, this time the goal was to minimize the cost. And so the solution here is the minimum cost is $11.40, and this is achieved by pill A, 30 pills, and pill B, 120 pills. Okay, here is the problem I'm asking you to turn in. A farmer plans to plant 2 crops A and B. The cost of cultivating crop A is $40 an acre. Crop B is $60 an acre. He has $7,400 available for land cultivation. Each acre of crop A requires 20 labor hours, and each for B requires 25 labor hours. And he has a maximum of 3,300 labor hours available. If she expects to make a profit of $1,500 per acre on crop A and $200 per acre on crop B, how many acres of each crop should she plant to maximize her profit? So I'm asking you to define your variables clearly as a part 1. State your objective function in terms of these variables in part 2. Part 3 is state all your constraints very specifically. Number 4 is create your corner point matrix and graph your feasible region. And point 5 is state your solution using complete sentences. I'm closing now, so I want to remind you that time is precious. Each day must count. Do the math. It will make you strong. Take care, and I will see you in class.